There we go. All right, so let's see, we're still missing Alex and Tyler. Give them a minute to show up. So last time we went over the decaplet. What happened with this? Are we still sharing here? You still see the iPad screen, all right? Oh, okay, yes, thumbs up, good. All right, so last time we talked about the octet and the decaplet, the various baryons that we find. And we looked a bit at the particle data group pages, which I really encourage you to browse. You know, just look up some particle, try and figure out, you know, what all information is there, and digest the fact that we've seen like hundreds and hundreds of particles, and it's those particles and their properties that are explained by the standard model. You know, like whoever hears about the delta plus plus or the omega minus or, you know, any of these arcane particles that are produced in particle accelerators, but they're seen routinely and distinguished from other particles by many properties. So there's actually a huge amount of data here to comprehend by this model. So when you see, yeah, I guess I sent it around on the email this morning. Y'all got that, I guess. I sent that usual picture you see of, oh, here are the 6 quarks and here are the 6 leptons, and then you've got the Higgs and the gauge bosons, and there's this, you know, nice colorful picture of the standard model. But in fact, it gets kind of complicated, and I've spent a fair bit of time honing my notes on this, trying to give the most logical development of the modifications that are required. But let's actually restart at the beginning. This is the end of the last recording, but what we did was to take the direct product of all the relevant groups. So we know we're going to want SU3, and that's SU3 color. And then SU2 cross, whoops, U1, and that's the symmetry of the electroweak. Okay, and you guys are seeing the screen, okay, the iPad. All right, I'll have to write smaller. Okay, I'm going to write the group quotient in an unusual way here like this. So we take the quotient by the Lorenz group and the SU3, SU2, and U1. And if you recall our general construction, what that does is it creates a manifold that is the difference in size between the upper group and the lower group. And the only difference is really Poincare over Lorenz, and that gives us space-time. And we ran through that. And then we have fibers that, in this case, what we've constructed is a principal fiber bundle where the fibers are actually Lie groups. And in this case, they're a big Lie group because each of these fibers is this whole denominator, right? There's the Lorenz group is sitting on that fiber, and the standard model symmetry is sitting on that fiber. So, you know, what is that? How big is this? The Lorenz group is 6 dimensions. SU3 is 8, SU2 is 3, and U1 is 4. So 8 plus 3 is 11, 12, and 6. So those are 18-dimensional lines right there. You know, use your imagination, or, you know, or draw something like 18 dimensions like this, and then remember those are all orthogonal to one another. It's hard to draw, but we know how to analyze each of those groups, so we know what to do.
Does
Okay.
that mean the numerator is 22 dimensions? Is that correct? How many dimensions?
Yeah, what
to
is
Poincare?
it? All right, this is 6, this is 8, 3, 1, which adds up to, what did I say, 14, 15, 18 dimensions. And this is 22 dimensions then.
Yeah.
The Poincare group is 10 and the Lorenz group is 6. Now, we can do this in any dimension. We could, build our standard model in 7 dimensions if we wanted to, and then the Poincare group and Lorenz groups would be bigger. We could put any groups we like on those fibers just by putting them both in the numerator and the denominator. But this turns out to succinctly describe what we've measured so far. Now, the standard model, I think I got into this a bit last time, but I'm gonna jump in my notes here to the standard model. I talk about the history a bit, and let's see, is this history section? Have you read it? Has anybody read the notes?
The history section, you say?
All right. The chapter 14 starts with a little bit of background to the standard model, and so let me talk about that a little bit. I think I talked a bit about it last time, so forgive any repetition here.
Yeah, I was reading through those this morning. I didn't get a lot of history from it though.
Yeah, it's it's just a couple of pages, and the development. It's worth understanding a bit of where this all comes from. The turn of the previous century, so 1900, right? You get quantum mechanics, you get general relativity, and with general relativity, there are 2 known fundamental interactions: gravity and electromagnetism. It would have been maybe the early 30s before it was realized there needed to be atomic structures. So once you had quantum mechanics and got the hydrogen atom, you start talking about heavier atoms, and there's got to be a strong force, because you now know that the structure involves a bunch of protons in a very small central region, and then electrons at 10 to the 4th times, 10 to the 5th times larger region. So in order to hold those protons together at the center, there has to be something out there stronger than electromagnetism. Gravity can't do that. So you predict right early on, there's got to be a strong interaction. Then with the discovery of the neutron, when was that? 32? Something like that. I don't, dates, doesn't matter. But the neutron is seen to decay into, at the time, a proton and an electron, and something else that came to be called the neutrino. For a while, there were actually 2 neutrons, and then someone suggested to Fermi that, jokingly, I think, that they ought to call the lighter one of the 2 neutrons the neutrino, the little neutral one. And so Fermi just started using the term, and that's what we call them today. So these are neutrinos, and we know there are 3 kinds of neutrino now. So all of that, but in order for this interaction to occur, Fermi proposed what's called the 4 Fermi interaction. So you have some interaction where you've got, all of these particles at the same place, actually an antineutrino, it can interact at a point, and basically you put the neutron and the proton. Let's see, how are these connected? Maybe with a gamma matrix. I forget the exact form of this interaction, but you can build these interactions where you have 4 of these at one place. And this doesn't really work, but it works really well. One of these is psi bar. But you build some sort of interaction like this that is a point interaction of 4 different fermions. And so you can turn that into neutron decay, something like this, where you get a proton, electron, and an antineutrino out. That actually is a pretty good description of the low energy weak interaction. But it turns out that the cross section goes up like as the square of the energy or something, and that does not agree at higher energies. And so a different model of the weak interaction was needed. Now, there was a lot of work on the weak interaction in the 50s, particularly Yang and Mills. CS, yeah, that's C and Yang. And Mills, I forget Mills' first names, but anyway, they were able to generalize some work from Hermann Weyl in around 1930, actually starting 1918. Weyl attempted to explain gravity and electromagnetism by including a gauging of the length of vectors. So general relativity involves gauging the Lorenz group, which is basically the rotations and boosts of Lorenz vectors. And Weyl allowed the length of the vectors to be gauged too, and that didn't quite work because it was much too strong. If you interpreted that gauge field as the electromagnetic potential, then any particles passing through electromagnetic fields would come out being different sizes. You were physically changing the size of things. And it was about a decade working on that theory before about 31, Weyl and a number of others actually, London and Fock, yeah, I've got it noted here, changed it to a phase invariance, and that gave the U1 theory of electromagnetism, which is essentially what we still use today. It's in a non-trivial combination with SU2, but so about 1930, you get e to the phi going to e to the I phi, and now we've got a U1 gauge theory. And that was the first gauge theory. Well, U1 is a billion. It's not too hard to write down what happens. And it was another 20 years before Yang and Mills were able to show how you could make local non-abelian transformations. So they gauged SU2. And that's Yang and Mills.
The screen doesn't seem to be updating.
Oh, did I lose something here?
I don't know, like there was a minute ago that it wasn't updating and then it did. But now again, it's not, because it seems like you're writing, but.
Yeah, I'm writing. Okay. I haven't written anything terribly crucial, a couple of dates.
I see Yang and Mills' name right now, and that's the last thing I see written.
But don't see, oh, well, isn't that disturbing? Let's see. Maybe I'll restart the share. Let's see if that helps. Let's see. Get this view. Okay, screen sharing. Share. And screen sharing. There we go. Okay. Do you see those dates now?
Yeah, that's updated.
Okay. All right.
It's live.
All right. So keep me posted if it doesn't. I can always share my computer screen and just go through the text, but that's
no, it seems to be working.
Not as fluid. So I'll try to, maybe if I keep moving this around or something, it'll be clearer. Okay, so yeah, was there a question?
No, nothing. I think it's fine.
You're good. Okay.
Yep.
So, okay, within like 2 years, Utiyama wrote a gauge theory describing gravity, electromagnetism, and Yang-Mills theories. You know, if he'd really known that the strong interaction was SU3 color, he could have written that down. He just wrote a general SUN theory, I think. You know, it's a nice paper, very succinct. Basically, he describes general relativity as a gauge theory too. That was the main import of that paper. The strong interaction was understood gradually over a decade. There was the essential point was noted first by a student of Bolyubov named Struminsky. And he commented on the existence of the omega minus particle, which is part of the decaplet. We've discussed that before. That's made of 3 S quarks. And if you look in detail about the orbitals and you know, ask for a ground state of this, all right, a ground state would be an S orbital, right? 0 net orbital angular momentum. The SSS is necessarily a totally symmetric state. The S state was symmetric. So in order to get an antisymmetric wave function for this fermion, you needed another symmetry. So he proposed that the quarks have an additional quantum number arising from an additional symmetry. And that was echoed 64, 65, pretty much the same year by Greenberg, and then a paper by independently by Han and Nambu. And they were, it was actually Han and Nambu, I think, who proposed an additional SU3 gauge degree of freedom. Later, that was called color. So this is not the SU3 that we get if we just look at the approximate symmetry between UD and S quarks. Are you seeing the UDS here? You're still seeing the screen? Okay. So, you know, SU3 color proposes that there is an additional quantum number that we assign to each quark, so that each quark comes in one of 3 colors. I think they're typically these days taken as red, green, and blue, RGB. Whoops, that's supposed to be a quark. Hello, quark. Okay. Are you seeing my notes now still? I'm suddenly worried that it's not sure.
No, we'll let you know.
Yeah, okay, great. Okay, so each quark, each of the 6, right, up, down, charm, strange, top, and bottom quarks, each of these comes in all 3 kinds: red, up, green, and up, blue. And same for all the others. And there's a symmetry, a color symmetry, that's SU3. So that symmetry will act on red, up, green, up, blue. The generators for SU3 are traceless Hermitian matrices, and they'll map into let's say up prime, green prime, and blue prime when you multiply that out. Well, so what this means is if we look at the generators for SU3, remember the Gelman matrices, we had things that looked like polymatrices. So we have things, this would be one of the Gelman matrices. And so if we have red, green, blue, what what this is going to do is give us, it's going to put the green up and the red down here and do nothing to the blue. Well, so if we start with just a red quark, so suppose we have nothing here, what you're going to end up with is nothing here, and you're going to end up with something in the green. So like 1 here gives you a 1 there. This is an awful mess. Let me clean it. So if we start out with a red quark field, we're going to end up with a blue quark field. So the strong interaction only changes color. It does not change the type of quark. And we're going to need a little bit of nomenclature here. So we have the different quarks. There's a perfectly good list right there. But these get broken up into 3s and 2s. So you've certainly seen the picture where you write up and down and charm and strange and top and bottom. But that doubling, the strong force doesn't care about that. In fact, the strong force can't change you from a down quark to a charm quark. You actually have 6 different quantum numbers that are conserved by the strong interaction. So there's a property called topness, a property called bottomness, a property called charm, strangeness. Each of those is conserved by the strong interaction, and that's pretty weird to think of. And it's mostly weird to think of because the weak interaction does not preserve that property. So what we're looking at here, this is weak isospin, and I think we discussed that when we looked at the octet and the decaplet, the different multiplets. But the third component of isospin can flip, and that takes you up and down in these doublets. This direction, whoops, tap my pen here. There we go. This direction is called either the family or the generation, either one. So when we're looking at the full list here, let me do it this way. U, B, S, C, T, B. All right, this is called flavor. Often written the British way with a U, but doesn't matter. You can write it any way you want. But we have 6 different flavors of quark, but they're divided into weak isospin states vertically and family or generation. I'll probably talk about the family, family 1, family 2, family 3, or generation 1, 2, or 3. That's a distinction that's made only by the weak quarks, by the weak interaction. Now, let's see, let me look at my notes here. Just to see where people went with this. This SG3 color was well established by the early 1970s. It was well, the latter half of the 60s and the early 70s when people proposed this SU3. Belmont called them quarks, and what was the other one? Called them aces. What's the other guy's name? There were so many people involved in developing all of this that, they don't spring to mind even sometimes. Now, in the early 70s, Salam and Weinberg and others, and to any name I give you, say, and others, developed the Electroweak unification. And that takes the SU2 that people were using for the weak interaction and the U1 that people were using for electromagnetism, and it combines them non-trivially. And that makes non-trivial predictions that are, so for example, the electrons in an atom can emit, say, Z0 particles, exchange Z0 particles with the nucleus, within the Electroweak theory. And we see that affecting the spectrum of hydrogen. So with the success of that unification, so the SU2 cross U1 theory of the electroweak interaction, that unification inspired others to look for further unification with the strong interaction. So theories that unify SU3 are called GUTS, Grand Unified Theories. And there were a lot of those. There are lots of ways to put all of these in a common group. So did I talk about the SU5 unification last time? You remember that? If you take SU5, so the generators of SU5 is in 5x5 traceless Hermitian matrices. And in the upper corner of, I think I ran
Yeah,
through.
I know, I remember.
Yeah, I'll say it briefly again. So those of you who were here last time will now remember it. All right, so, you can put an SU3 up here. And in this lower 2x2, you can fit an SU2. And then if you have something that looks like the identity up in the 3x3 part, let's make that a one up here. And then you've got to make it traceless. So you're going to need -3 halves down here, just a multiple of the identity down there. That commutes with these. That commutes with the SU3 and the SU2. So that gives you a U1, and you've packed all three of the standard model symmetries into an SU5 matrix. Now, the problem with that is you're predicting the existence of 6 more particles called X's and Y's, and their conjugates are over here. These X and Y particles have a funny property. If you've got, say, an X here, let's just be cryptic about the rest of this. And what do these act on? Well, the SU3 acts on quarks. So you've got a red, green, and a blue quark of some sort. And then you've got a lepton and lepton neutrino as a doublet that the SU2 acts on. But then if you take the conjugate to that, Q bar, Q bar, Q bar with an L bar, neutrino bar over here, that would be a typical interaction for this. So you have a generator of SU5. This is a lot like if we had the Pauli matrices and say 2 component spinners, you might have an interaction term like that. We've seen things like that before. Well, here you have this generator sandwiched between fermionic multiplets with 5 particles. Well, look what happens with this X particle. That's going to pick up this lepton, and then when we bring it over here, it's going to pick up this red quark. And so we have an interaction term like this. Now, when I write something like this, you should be thinking of something like our electromagnetic interaction for QED. Remember, we had an A/psi like this. We had a term like this that came from the gauge theory of U1. And this is a coupling between 2 fermions and the photon that gets a Feynman diagram that looks like this. So this predicts a certain kind of interaction. We have, say, an electron going in and coming out, and a photon going away like that. Well, this kind of interaction says we've got a lepton, say an electron coming in, and it emits an X particle, and the quark goes out. Well, that's weird. Usually you might think of it the other way, since quarks are more massive than electrons. You can have a quark emit an X particle and turn into an electron. That means that hadrons can decay into leptons. And in particular, the most stable hadron we know is the proton, and this would lead to proton decay. A proton could decay directly into an X particle and an electron, or a positron, of course, to conserve charge. And so you have to say, well, you know, are there limits on the masses of these X particles that would suppress this interaction? And yes, there are limits. They could be very massive, not arbitrarily massive. And if you work out the upper limit of the mass on those by hierarchical arguments, then you find that the protons still would decay in about 10 to the 30th years. And they don't, because we've measured that. Proton decay is known to be, they last longer than 10 to the 31. One experiment shows it's longer than 10 to the 33 years. So that particular decay doesn't happen. And maybe you can modify the theory some way that would make it work, but that particular unification isn't so hot. But you can use SO10, or, well, you know, you could use SO87, and that's big enough to contain SU2 cross SU3 cross U1. So, you know, there are infinitely many choices for a grand unified theory. And people also tried to do what are called TOEs, theory of everything, TOEs. And these are commonly used notation, a gut or a toe. A theory of everything includes gravity in the mix. And as I think I said at the end of the last lecture, yeah, sorry, Guillermo and Kevin, I know you heard this, but it turns out that you can't really do it. You know, if you want some group where you can stick the Lorenz group up here and the standard model, some kind of a gut down here, it has to be a direct product. Coleman and Mandula proved a theorem that showed that the only way to do that is with zeros here. You know, and they showed that by asserting a short list of pretty natural properties that any quantum field theory should have. So it's a very powerful theorem. And the only, well, not the only way, there are a few ways around it, but the most commonly pursued way around it was to allow some of the generators of the algebra now to satisfy anti-commutation relations. So these would actually be fermionic generators. And a fermionic generator is going to mix different spin particles. So you'll have symmetry transformations that add a little bit of your electron to your photon, or something like that. So you've got different spin fields that map into one another. There are drawbacks of those, but there are advantages. That pairing of fermions and bosons actually makes your quantum field theory diagrams converge better. It gives a lot of cancellations. So there are a lot of nice things that come from doing this. One fairly compelling thing that you get from super gravity theories, because, you know, with these anti-commutators included, you're dealing with something called a graded Lie algebra. Graded Lie algebra. And using those, you can include gravity and build a TOE. So in the late 70s, people were working on on supergravity theories, where you would you'd have multiplets with a graviton, which is a spin 2 field. You would have what's called a Rarita-Schwinger field. You would have you'd have some vector fields. You would have some spinor fields and Skiver field, and the symmetry it can mix those, not entirely. You still have some independent parts of these, just like with electromagnetism. You have you do a gauge transformation of the vector potential, so it's not physical, but its curl is physical. So there's still a physical part to these fields. Well, this Rarita-Schwinger field is a spin 3/2 field. And we haven't seen any, but they could be there. But in order to make a spin 3/2 field consistent, you get aphysical behavior unless you add in some constraints. And people, Rarita and Schwinger and others, worked out what these constraints needed to be in order to make a spin 3/2 field consistent, just internally. Well, it turns out that supersymmetry imposes exactly those constraints automatically. As a part of the supersymmetry, those constraints just hold. And that lets one feel at least like supersymmetry is the right idea about something anyway. Now, there's a drawback to supersymmetry, because in these super multiplets is what these are called. It turns out that the supersymmetry generators, they're written something like this. The anti-commutator of these gives a translation generator, the momentum generator. And that implies that the supersymmetry generator, which, all right, it's actually these Qs that take you mix up and down in these multiplets. These supersymmetry generators commute with p squared. And I think this comes just out of the Jacobi identity, the super Jacobi identity. You have to be very careful with signs. This stuff's tricky, but don't despair. I know a USU graduate student who, actually mastered some of this stuff, so it's not impossible to get. But what this means, right? P squared is the mass squared operator, and that commutes with the supersymmetry transformations, which means that all the particles that you put in this multiplet have to have the same mass, because Q can't change the mass. And that has put a bit of a damper on some investigations of supersymmetry. What people do is suppose that the supersymmetric partner, if I've got a supersymmetry that relates a vector field and a spinor field, say, so I've got a supersymmetry that does this. You suppose that one of these two particles has a very large mass and we haven't seen it yet. And one of the criteria for the Large Hadron Collider is that it should be able to see those very massive superpartners. And that would be concrete evidence for supersymmetry if the interactions were borne out appropriately. Well, we haven't seen that. And there are real questions about whether supersymmetry is really going to hold up. And you all talk to Eli about that, because he's going to solve that problem. All right. So one further step in all of this. All right. So we have supergravity theories. Supergravity tows. You still have the problem of That's the problem. I forget what the problem is. Oh, of what group to use. All right, so, you know, you could supersymmetrize, you know, SO93, right? And so you supersymmetrize that and, you know, you've got some theory of everything, except that you don't know what to do with all the rest of it. Now, making it super actually puts a restriction because 11-dimensional supergravity is the maximum that you really expect to see. There have been arguments that we shouldn't see anything in fields with spin higher than 2. There are some inconsistencies or best difficulties associated with higher spin fields. And I know Deser has done some work on that. So you don't want your supersymmetry multiplets to go higher than spin 2, and that limits them to 10 or 11 dimensions for a consistent supergravity theory, but you still don't know what the group is. Okay, there was a parallel development, Nambu and Goto. In 1968, we're looking at mesons, and that's a strong force between a quark and an anti-quark. So there are quarks that are, you know, red and green balls, right? And then they're exchanging gluons like crazy. So it's such a strong force that the lines of force, you know, thinking classically here, the lines of force are very tightly down to a line between the charges. And so what they thought they would look at is, what if you had a piece of string with, you know, say a, you know, red and green charges on the end, or whatever other quark properties you need on the ends, but can you predict the spectrum of mesons from the spectrum of a piece of string? And what that would mean is that, okay, you have a piece of string and it's maybe spinning end for end here, and that puts some tension so you can have oscillatory modes of the string. And, you know, we're at very high energy here. So if you make this thing oscillate a little bit faster, its energy is higher, so its mass is a lot higher. And you get a mass spectrum of different oscillations of this bit of string. So they worked this out, and they found, well, you know, what you do. And, you know, I'll talk about this later if we have time, especially if Alex gets around to rejoining us, because she seems to be interested in this. But all right, you write a solution for string. Well, what is it? Well, you've got a position, and you've got some initial momentum, velocity, and then you have different modes of oscillation. So for each n, you've got some amplitude, e to the I, and times time, and maybe sine pi x over L, so, something like this. You can expand the string in modes like this. And so that gives you the space-time position as a function of time. And let's see, this x, let's call that sigma. That's a parameter running the length of the string. So you have a coordinate that depends on 2 parameters. So, you know, we know how to quantize x of t, right? You have a world line of some particle, and you just do standard quantum mechanics with that. Well, this is not very different. You quantize this thing, and what happens in field theory, right, is each of these things becomes an operator. In particular, now you have this infinite tower of operators. For each integer, you actually get a pair of them. And From those, you can build, let's see, I forget how it goes here, something like, if you put this with the conjugate one, and sum that over n, you get some rank 2 tensor operators. So these are operators. And it turns out that from the operators of the string, you can construct operators that satisfy the Poincare-Lie algebra. And what that tells you is if you're going to have some spin 2 modes, and they're going to generate general relativity, because from the quantum operators, or from the operators that describe quantum string, you can build operators that satisfy the Poincare-Lie algebra. And that tells you that at least the low energy gauge theory is going to and a spin 2 mode. Well, it was Shirk and Schwartz who then explored those spin 2 modes as a theory of gravity, and showed in 1976 that while these models didn't work all that well for the mesons, they do work for gravity, and they do give you general relativity. And finally, then in 1984, Green and Schwartz showed that there were exactly 2 possible symmetries, internal symmetries associated with string, with superstring, SO32 and E8 cross E8, which are very large groups, but the group is semi-unique. So instead of having any Lie group as a possible grand unified theory, now we have either E8 cross E8 or SO32 as a candidate grand unified theory for the standard model. This all happens in 10 dimensions, as I'm sure you've heard, and you then have to find a way to get down to 4 dimensions and understand what all the other excitations in that model are. And there's a lot of work going on that. So that's how we got from all of this to string theory. We're not going there yet. Let's get to the standard model, which is really the best verified model we have ever had. It has survived, I don't know, gazillions of experiments, predicted many properties of all of these excited states, of the many particles in the decaplet and the octet, their excitations and so on. So we know a whole lot about hadrons and weak interaction. And so that's what we want to focus on going forward. Now, let's see, way back here, before I got distracted by all this history, we wrote down, we wrote down this quotient. And this quotient is a principal fiber bundle that has the symmetry we want. We're going to leave space-time flat. Okay, and we do the usual thing. We write the Maurer-Cartan equations for this. This gives us gauge fields. And I've given you some exercises down here somewhere, I think. But we know the generators for these alphabets. We have the Belmont matrices for SU3. As SU3 generators, we have the poly matrices for SU2. And we know the Lie algebras for this, right? The poly matrices, of course, satisfy Y, epsilon, I, J, K. So we're dealing with just the 3-dimensional Levi-Chitov tensor. Not a hard thing to work with. I hope you're feeling comfortable with that one now. And then for the Belmont matrices, there are some structure constants, F to B, to C, and these are totally anti-symmetric as well, as it happens. There are a bunch of those, but they're not too hard to figure out. And then we have the Lie algebra of the Poincare group, which I won't, it's in the notes. You can read that in the notes. But then there's one more generator for the one. There's a single generator called Hypercharge. And this isn't quite the same definition. We gave a hypercharge when we were looking at flavor symmetry, but it comes out in pretty much the same places. So then we define some one forms dual to the generator, the Pauli matrices. Here we have three one forms. These are one forms. So the algebra valued one forms. These are connections. These are the gauge fields. Okay, these one forms are just like the vector potential for electromagnetism, but these are the gauge fields that arise from the SU3 and the SU2 and so on. Then we have a dual to the Belmont matrices. We have some one forms, one for each generator there. And then we have the equal Poincare dualities. This solid. We're going to leave the space flat so we don't see much of the place. We're going to make these fields local. And that'll be on flat space time. Well, we write the Mallet-Cartan equations for these. So for example, we have B, that B is 0, and we have B is the B. Would be C for the polymetric. So we have minus a half structure constants.
It's a slightly new issue here.
Yes.
Or at least on my end, the mic is getting muffled or something like that. Sometimes you're clear and sometimes it sounds like I can't hear you.
All right. So yeah, let me let's see. Am I clear now?
Oh yeah, you're good right now.
All right, I'll talk toward the computer. That's
Okay.
If I talk over here, it's probably muffled, and if I talk there, you're okay.
Yeah.
All right.
Yeah.
I'll try to look at you when I talk.
Sounds good.
Then for dB, we're going to have J wedge BK. That's what the Mallet-Cartan equation always looks at, where these are the structure constants here. Then for the G's, minus a half F, let me see, G, B wedge G, C. Okay, so these are the gluons. And these three particles, well, these four particles are the photon, the W plus and minus, and the Z naught particle within the unified electroweak model. So we've introduced these, then they have field strengths. When we modify the connection, if you're remembering our general procedure for gauge theories, then these change. Then we have some fields here. Let me see what I've called the fields. This one, so this becomes some field H. Here we're going to have, let's call it Fi, and here we're going to have GA. And those are the field strengths, like the Faraday tensor for electromagnetism. Those are the field strengths of the gauge particles. So the gauge particles are bosonic. These are all vector particles, like the photon. And the vectors are going to be, we'll have B and U for this one, and we'll have G mu A. So each of these is a collection of vector particles. When we draw Feynman diagrams with these are wavy lines. The gluons are curly Q lines. Like, right. So then we can expand out what these fields look like. So, all right, I did this in the notes, and I gave these other two as just an exercise, but it's easy to write these in components. These fields are Lie algebra valued 2 forms. So they're second rank space-time tensors, anti-symmetric, and there's one for each generator of the group. So for this gluon field, there are going to be 8 different fields. And they end up looking like d alpha of G A beta curl. And then you also have the structure constant. So this is the thing that makes non-abelian gauge theory a little tricky. You've got these additional B alpha G C beta. So this is what the gluon field strengths look like. You do pretty much the same things with these that you do with any of the that we did with QED, and so far everything we've done is just mathematics. We've created a fiber bundle that's got the symmetries we want, so that we can define fields with local symmetries. Now what we need is an action. And constructing the action for the standard model, there are some surprises. I think I alluded last time to the real difficulty that one encounters. Let me not get ahead of it. Let me list the possible things that we can put in this action first. So there are tensor from the original model. So we've got the field strengths of the 3 sets of gauge particles like this. We have the solder form, or we could use the either the orthonormal form or we have the Minkowski metric. We could use the Levi-Civita tensor. All of these are tensor fields that are naturally there on our structure. We've got the Lorenz invariant tensors. We're not going to add curvature, but we could. But we have curvature of the gauge. But then there are some other things we can do. So for the Lorenz symmetry, we're going to use actually spin 3-1. Spin 1-3. That's a way of writing the Lorenz group where we know how to take a covariant derivative of a spinor field. So instead of SO13, we do spin 1-3, and that's just a representation of the Lorenz group that knows how to differentiate spinors. From that, right, that involves the gamma matrices, and from those we can produce various bispinors. So if we sandwich a gamma between a couple spinors, something like this, that's some sort of vector valued object. If I make both of those psi, that's a Lorenz vector built out of spinors. We know how spinors transform, so that will induce the way that those vectors transform, and they transform like vectors. We can build other things. We can sandwich all right, sigma, remember, is the commutator of 2 gamma matrices. those are generators of rotations, but we can build tensors out of those. So basically anything that we can build using the basic gamma matrices of the Clifford algebra. Remember, we got these guys. So anything we can build out of those in spinors. Well, we know what we can build out of the gamma matrices. We have 15 things. I don't know what that line was. Did I just change color? No, guess not. We have one, and we have the gamma matrices. We can take the commutator of gamma matrices. We can take a gamma matrix with gamma 5, and we can take gamma 5. And that's 16 different matrices that span 4x4, all 4x4 matrices. And we can now combine those with spinors and build various tensors. Anything we can build that way, we're allowed to put into the action. So, it's not uniquely determined. There's plenty of flexibility. That's what we get from the Lorenz symmetry. Then SU3, we have various colors. And so let's see, be either red or green or blue. And let's see, so what can we build out of those? Well, anytime, all right, these span a three-dimensional vector space, and the color transformations act on that three-dimensional vector space. Anytime you've got, all right, that's called a representation of the Lie group. A vector space on which a group acts is called a representation. We're dealing with linear representations, so we're talking about vector spaces that the group acts on, and that implies we need to write the transformations of the group as matrices. Those vector spaces have associated tensors. Right? If I have some vector, I don't know what index to put on this. I'll just use I. But some amount of red field and green field and blue field, then I can take outer products of those and form second rank tensors. And I can add together linear combinations of outer products of such things. And I can build any matrices I like, and I can build any higher rank tensors by taking more outer products. Well, that's not quite what we do. We've already done this with the Young tableau. So we can take products of these, and we know that if we take a product of 3, for example, there's a singlet, and there are 2 octets, and 2 of those, and there's a decaplet. So we've already run through that and identified various particles with them. Well, those particle identifications hold up, only it's color now that gives rise to it. So this partition of these outer products, these are the irreducible representations, and those transform within themselves in a more coherent way. They don't mix with one another, so it's a more natural way to write tensors over a given vector space. That's why we use spherical harmonics when we're doing electromagnetism. Those are irreducible tensors in which we can express the various fields we encounter, and that's turns out to be more useful than just taking these arbitrary products, because there are parts of those arbitrary products that don't ever mix with one another. So we can do that with any of the vector spaces. So we have a 3-dimensional vector space. We can build SU3 covariant tensors from these vectors. Then we can do the same thing for SU2 and for U1. Now, for SU2, the basic representation is a pair. So the weak interaction is always going to be acting most fundamentally on these pairs of fields. But there are scalars. You know, if this is we could take an inner product of two of these fields, and that's some kind of a scalar. We can take outer products and form higher ranked tensors of these under SU2. So tensors under SU2. And then finally for hypercharge is just a scalar. So if we have a field that has, let's see, hypercharge Y, then under transformation, let's see, right, if we have a group element G, that's an element of our U1, then G is going to act Y times. So it's just a factor, right? So it's going to act Y times on a field of hypercharge Y. So we can use any of these things in the action. So we're not just going to throw these in willy-nilly, although actually, come to think of it, in the 60s, I think people did look at like everything you could build out of these guys, right? Tensor interactions and pseudo-scalar interactions and things like that. People did accelerator tests if any of those characterized the interactions that are happening. And so we're able to settle on which ones actually do happen. The ones that actually do happen are well described by the gauge covariant derivative. Remember in electromagnetism, we had a derivative of a charge field that was the usual derivative and then the gauge field times the field. Well, in general, what you have, suppose we wanted an SU3 covariant derivative of some color multiplet. Let's let capital A be 1, 2, 3. And we are going to run into trouble with indices here because there aren't enough different alphabets around. So you would take the derivative, and then you have the connection, and let's see, it's unitary. We probably want an I, but now we have the gluons, G alpha, let's see, and then for each generator, you can put the generators here, and the generators form a matrix, and that matrix acts on psi. So this is the way you form a covariant derivative. Well, these generators are just the Belmont matrices. So using your connection one forms, one for each generator, and making it explicitly a Lie algebra valued one form lets you write a covariant derivative. So this derivative will be covariant with respect to SU3 transformations. So I can apply an SU3 transformation to that psi A, and this derivative will still give me the right thing. That can be any local SU3 transformation. Now, what this gives couplings. So if we were to write like the Dirac equation with this derivative acting, minus I times that derivative minus a mass. So suppose we had this term in our action, where now these, remember, are, they're SU3 triplets. So they're red, green, blue fields. So there are 3 components to that guy, and each of those components is a spinor field, right? There's a lot going on here. We're going to be dealing with, I think it's 4 different spaces at once. So I didn't warn you. I told you, lots of spaces at once. Usually we can deal with like one or two at a time, so it's not nearly that bad, but it gets complicated. Okay, so what this kind of term does is it includes this extra gauge stuff into the theory in a very precisely predicted way. So we've got minus I, G alpha A, lambda A is a matrix that acts on these two multiplets. This is an interaction, right? That says you've got a psi particle coming along and it's going to, oops, it's really low, pigtail. It's going to emit that gluon field and, you know, go on its way is probably something of a different color, right? Because all these can change as the color. So if this is red, this might be green. And instead of labeling these G alpha as A, it's actually convenient to label them, say, a red anti-G, and well, or in the present case, a green anti-red would annihilate the red and leave a green because this carries off the green and annihilates the red. So we can keep track of the gluons that way. I thought Kevin was really pleased at all this, but that's just his picture there with a nice smile. I'm sure he'll join us. Let's see. All right. So, you know, don't panic over the labels, but you know, we'll try to look at one interaction at a time so that it's you know, it's clear what the various indices refer to. Okay, so let's just try an action, and there's a fairly natural thing to write. Okay, so for a Yang-Mills field, something like the trace of the field strength wedged with the dual of the field strength. You know, like, what is that? Well, remember what these one forms are. These one forms are really Lie algebra valued things, and they have space-time indices on them. And so what we're doing when we write something like this, if you work out the dual, you find you're contracting the Lorenz indices, and the trace of a product of those two matrices gives what's called the killing metric. And in the case of SUN, that's just the identity, the Euclidean metric. So really what this action is, up to some overall multiple, I think it's a quarter here, we're summing over the 8 different gluon fields. And you can, when it's a Euclidean inner product, you can write them both in the same position. And then we sum over the Lorenz indices in the usual way. And we have a D4X here because here we are in space-time. So our action is, you know, it's just like the Faraday squared action for electromagnetism, but we're also summing over the 8 different gluon fields. So that's a natural generalization of the thing that you know, what we already know from QED. Now,
Great question.
yes.
In the notes where you define the same action, you leave the wedge out. And is that significant, or is that a typo?
I should probably put it in the notes. It's anytime I write 2 differential forms next to each other, there's a wedge product.
Implied. Yeah.
There's always a wedge product. Yeah. Yeah. I should stick that in. Yes, that's a wedge.
Well, now I know too. So yeah.
Yeah. Yeah, you know, when you're doing research with stuff, it's, you know, just tedious and makes your expressions twice as long to stick in all the wedges. But they're there. And, you know, by the time you write something up, you should stick in the wedges. Okay, so we've talked about the families of the 6 flavors of quark and leptons, but now an action for the quarks, right? So this is the well, this is the SU3 gauge fields, but then we have a similar thing for the hypercharge and for the SU2. And again, it's a Euclidean inner product here, so I can just sum the internal symmetry index in the up position. There's a sum on I here. There's a sum on A here. All right, now for the fermions, we expect to use a covariant derivative, and we're talking about Dirac fields, so we're going to contract those with gamma matrices, and we'll have an I minus M, and that's going to act on some multiplets of fields. So for each spinor field we introduce, we're going to have some action of this form initially. That we're going to have to modify this, but you know, if we this is a nightmare if you actually put in all the indices that might be here, because all right, so if we're talking about quarks, our initial stab at an action for quarks is going to be what? We're going to sum over color. So color can be red or green or blue. And we're going to sum over the weak isospin. So I is going to be 1 to 2. And we're going to sum over all the flavors. And the flavor can be, well, generation 1 or 2, or the family, 1 or 2 or 3. And then what we have, all right, psi bar. So what is this? Well, it's got a spinor index A, and it's got a color associated with it. And it's, you know, up or down. It's got an isospin associated with it. And it's got a generation or a family. And then we have gamma matrices with a covariant derivative minus M. And except if I'm going to put in the spinor index, then that gamma mu is really some matrix like this. And I have a psi B over here. And that also has CI and F indices as well. So we're summing over all of these different things. Well, what have we got? We've got 3 colors of each of the 6 quarks, you know, like 18 different fields we're introducing here. But there's so much symmetry between them that, you know, you just write one psi and you know that that's representing, you know, pretty much any of these different things. So we'll avoid writing too many indices. Okay, so there are some problems with this picture. You know, we can write a candidate action here, right? So, so if we just write the strong Lagrangian, let's see, what are we doing here? Yeah, all right, we might have a sum of over the different gluon fields like this. And then we have a sum over colors and a sum over, well, let's just say all the quarks of the different quark fields and the different colors. So we have something like this. Now, that's actually not too bad, because the gluon fields do just what you think. They change the color of the given quark. And so what you get are Feynman diagrams where I could do this in, I've done this in color in the notes, which I'll post soon, but you could have, say, a green D quark, Ooh, that was cool. So I always do that. It turned it into a perfect circle. I don't know how I did that. Oh well, it'll never happen again. All right. So suppose this emits a gluon that is a green anti-red gluon, and that's a vector particle. And so that happens with a probability that depends on some coupling constant, little g, and there will be a gamma alpha here because that's the kind of coupling that we've introduced. And so we've, the green is carried off here, we've got anti-red carried off, and so this still a D quark here, that better be a red quark. So we've changed a green quark to a red quark. It's simple and clean, and this is pretty much what happens with the strong interaction. Now, this is not the only thing that happens with the strong interaction. Let's see if right, before I say what else happens, let's look at. All right, this is the simplest term. So what I'm writing here is, all right, we've got a say a red quark coming out. We've got a term here that's got a gamma matrix, and it's going to have G mu, a green anti-red gluon field, and it's going to have a green quark annihilated, or going out with the gluon. So in this covariant derivative, we have a term of this form. And that describes the way that the gluons interact with the fermion fields. And that's it. So it's just like electromagnetism, except you've got a whole lot of these particles. They're, as far as we know, they are massless. And so here we can, no, the quarks are not massless, sorry. The gluons are massless. There is a point to stress here. With these gauge fields, the gauge fields you always expect to have massless because you cannot add our usual mass term. So if we have a couple of these gluons, and let's combine it, say, with a red anti-green to have no net color, and we put a mass squared there. So, can we add a term like this to the action for the pure gluon fields? Well, we can't, no more than we could add a mass to the photon. Remember, the photon, if you wanted a massive photon, you would add a term like this. That breaks gauge invariance. A changes by a gradient, and so in a different gauge, whoa. Alex is joining us. Alex, hello. Can you hear us?
I can. Hi.
Well, welcome back. Long time no see. I hope you've been able to catch up with some of the notes. How are you doing in the reading? Silence.
I've been through.
You're totally up with it, right?
I don't know. I read the first 2 sections of Peskin, so if we're there, then we're there.
Yeah, no.
Probably none of this.
Okay, so see if you can't catch up with the lectures. That'd be nice. Send me questions. All right. Anyway, if we gauge the electromagnetic field, it changes inhomogeneously. Every connection changes inhomogeneously. That's what it's for. But that means that a mass term like this is not gauge invariant, so you just can't add it. You cannot have masses for the gauge bosons. And that's not a problem for the strong force. The strong force really, as far as we know, behaves itself. It acts like just a nice, clean SU3 gauge theory, doing all the things that SU3 gauge theories can do, which there are more, and I'll show them in a second here. But the weak force mucks it all up. So we're going to spend a lot more time talking about the weak interaction. But let's look at this action for the strong force. The connection to the quarks is simple. It's just like the photon vertex behaves very much the same way. The only difference being that our perturbation's no good, because this, whoops, where'd it go? This G, the coupling constant that goes here, with the electromagnetic force, that ends up giving you a contribution of order of the fine structure constant when you look at interactions. And so your Feynman series perturbative series converges fairly quickly. But this G is of order 1, not 1 over 137, so you barely get any convergence at all. So higher order diagrams are pretty much just as likely as first order diagrams. Okay, what else can happen? If we expand the gluon fields, remember that the gluon field is a curl G beta G alpha A plus a structure constant G alpha B G beta C. And this term means that there are going to be other interactions. This curl term is just, that gives rise to the propagator. That just means that your gluon goes from here to there. That's all you do. You draw a gluon line. But now we're going to square all of this. And so we're going to get a product of that kinetic term with this structure constant term. So we have a D alpha G beta A minus D beta G alpha A and F A B C G, probably going to contract alpha B G beta C's, something like this. You have to anti-symmetrize this over the ABC, and you know the constant that does that gets, you know, it's a whole bunch of metrics and structure constant things. But this leads to an interaction where you have two gluon fields, these two, and a derivative of a gluon field, all coupling together. So it's a three gluon interaction. And so now if your quark is coming along and emits a gluon and goes along as a quark, that gluon can produce a couple more gluons, which can go on and they can produce a couple more gluons if they want. Of course, a couple of those gluons can combine to form one. So you can develop this whole field of gluons, and that multiplies. What happens is that eventually one of these gluons will produce a quark anti-quark pair. And let's see, so if we had, say, suppose we had an anti-quark going along that did this, that quark and that anti-quark are going to form a meson of some sort. And this quark is going to go off and join some other quark eventually. What happens is, as you put energy into quark interactions, you produce more and more gluons, and what ultimately comes out are floods of mesons. So when you're talking about the energy at the LHC, you could have 1,000 mesons come out of a single quark-quark collision. Right? That's not all that happens, because you also have, let's say, FABC, FADE with GB alpha, GC beta, GD alpha, GE beta, with various anti-symmetrizations happening here. This is a 4-quark, 4-gluon interaction. So we also have a Feynman diagram that looks like this. And these, because of the symmetries of just really the Lorenz symmetries, we can rotate these any way we like. So we can have 1 gluon come in and turn into 3, or we can have 2 turn into 2, or we can have 3 turn into 1. You know, any way you want to rotate those different gluon lines is allowed. So so the strong force, and in fact, this is true of any non-abelian Yang-Mills theory, because non-abelian Yang-Mills theory, as you'll see when you do these, let's see, where did I, oh, let's see, we're covering ground like mad here. Oh, there we go. Yeah, the fields are always going to be a curl of the gauge field plus a structure constant with a couple more gauge fields. Anytime you have a non-abelian field, you have this quadratic term, and when you square that with the usual Yang-Mills type action, you're going to have cubic and quartic interactions. So these diagrams, this 3-particle diagram and this 4-particle diagram will, now what happened? Oh, there it goes. So that will accompany the usual interaction. What did I do with it here? Oh, there it is. Okay, let me just put them all together. So in addition to the usual interaction with the quarks that comes from the covariant derivative of the spinor fields, any non-abelian gauge theory is going to also have cubic and quartic interactions. So the gluon ones look like this. For the weak interaction, you just have wavy lines like that, but the basic upshot is the same. You have a lot of possible diagrams and interesting questions of convergence and all of that. So that gives us the basic action we're going to start with. And as I say, that's the strong interaction is pretty straightforward except for the strength. So making predictions from the strong interaction, what typically will happen is you get jets. You don't just make one other particle turn a neutron into a proton or something. What happens when quarks collide at high energy? If you have a strong interaction, you're going to be producing hadrons, and they'll come off in 2 or 3 dominant directions. You've produced some heavy hadrons, so they decay really rapidly into like a flood of other particles via the strong and then the weak interaction. And what the initial directions of those 2 or 3 hadrons ends up indicated by this flood of hundreds of particles coming off in a particular direction. If you add up all the momenta of all of those particles coming out, you do basically a sort of calorimetry. You try to collect all the energy of that jet, and that tells you the energy of that initial baryon or meson that you've produced. So that's more or less how you detect these things at high energy. Now, the electroweak interactions pose a whole different set of problems, and they even muck up the strong interactions. So one thing that happens with the weak interactions is that they violate parity. Now let's see. How did we learn about this? It was really oh, there's a great story about this. Okay, story time. Chandrasekhar used to tell this story. It was his favorite story, and in 1983 he got to modify it when he received the Nobel Prize. He says there was one time that he taught a class, and every student in the class and the professor got Nobel Prizes. The class was taught. He was working at Yerkes Observatory up, I think it's north of Chicago. It's an hour or two from Chicago, and once a week he would drive into campus and have a meeting with 2 young students who wanted to learn some general relativity, T.D. Lee and C.N. Yang. And Lee and Yang, that was probably, I don't know, the late 40s, early 50s that they were students there. But within a few years, they made a prediction of parity violation in the weak interaction. And they met together with Wu, C.S. Wu, Chang, I forget her name, but designing some experiments to test for parity violation in the weak interaction. And she found it, and they got Nobel Prizes. And that's generally regarded as one of the greater errors the Nobel Committee has ever made. She did get the Wolf Prize eventually, but she did the experiment. If that had happened, this was in the mid-50s, the 1957 Nobel Prize was awarded to Yang and Lee. If this had happened now, the Nobel Committee generally awards prizes, well, certainly only when a theoretical thing has been detected, has been actually measured. And the head of the experimental group is the first to get the award, and then they may pick up a theorist or two who predicted it. That's happened with the Higgs. All right, the head of the LHC group that saw the Higgs, along with Higgs and who was the other one who got the prize with Higgs? I think one of the other theorists. There were 5 or 6 people sitting around the table at lunch when they dreamed up this symmetry breaking thing for the Higgs, and but Higgs and maybe Engler, I think it was Engler, and then the head of one of the leaders at the LHC. But the LHC the paper that announced the Higgs had 3 pages of authors, right? I mean, you know, these things just always are done by a lot more people than the ones you ultimately hear about. So anyway, let's take a look at Wu's experiment, right? So the first thing is how you might detect parity. And if we look, are you still seeing the screen? Okay. Imagine a particle with momentum p and angular momentum vector s, like this, where the momentum vector, the spin is quantized. You can quantize it in some direction. So let's choose the direction of its momentum. We're going to stay in 1 Lorentz frame, so it doesn't matter that this is not a Lorentz invariant quantity. We're just, you know, in the lab. So this would be a positive helicity, you know, right-hand rule on the direction of the angular momentum. And if that aligns with the momentum vector, you've got positive helicity. If you apply the parity operator to this, then the direction of the momentum vector changes. So parity applied to position, all right, it changes the spatial position to minus the spatial position. And so dx dt is going to change as well. So the momentum changes, but angular momentum, well, certainly orbital angular momentum, r cross p, right? P changes sign and r changes sign, so angular momentum does not. And we take spin to behave the same way under parity. So the spin stays the same. And there we have the key to a way to detect parity violation, because if there's some sort of non-trivial coupling to the spin in an interaction, then you know, we can detect it by the relationship to the direction of the motion and see some evidence of parity violation. So, right, parity conservation holds if the mirror image process occurs with the same probability as the process itself. So if we detect these with equal probability, then parity is conserved. Well, you know, how would you know? First, you need something where there's some sensitivity to the spin. So what Wu and her colleagues did was to look at Cobalt 60. And Cobalt 60 with 27 protons decays into an excited state of nickel, 28 protons and 60. So, you know, what we're looking at here underlyingly is a neutron going to a proton. And so you expect to see an electron and an antineutrino come off. So you do. Antineutrino. But this is an excited state of the nickel, nucleus now. There are probably no electrons in the problem. These may be, well, I don't actually know how the experimental setup worked, but this is what they were doing. But the nucleus was an excited state of the nickel nucleus. And that excited state of nickel decayed to a non-excited state of nickel plus a couple of photons. So your overall interaction is Cobalt 60 decaying into nickel and a couple of photons and a couple of leptons, like this. And now here's the way they were able to get a comparison. If you just had a gas of the cobalt, then you would get these particles coming off in just arbitrary directions. So what you want to do is polarize the Cobalt 60. So you want to get the cobalt atoms angular momentum vectors lined up as much as possible. Well, they were able to do that. It produced a certain asymmetry in the radiation of the photons, right? They got about 40% of the photons one way and 40%, 60% of the photons the other way. So they established an asymmetry of the radiation, and that's based on the spin of the photons. But okay, that's an electromagnetic decay. Electromagnetic decays are known to preserve parity. So those photons came off in the directions of parity producing particles. And so what they did was then to look at the distribution of the electrons. They could look at the neutrinos, but to see if the distribution of electrons was the same as the distribution of the photons. And it's not. It comes out decidedly different than the photon directions. So that tells you that the electron, the weak decay that produces the electron is producing a different distribution than the parity preserving electromagnetic decay that produced the photons, and therefore the weak interaction violates parity. That messes everything up. This was a shock. So was it Pauly, I think, said, "Oh, well, the experiment's wrong. Redo it." I mean, people thought parity was conserved, period. But it's not. And this has been verified by, I don't know how many other experiments, but it's actually quite an industry to find parity non-conservation. It turns out that the weak interaction also violates charge conjugation parity. So if you take the conjugates, complex conjugates is charge conjugation, right? So if you take the conjugates of the particles in a weak interaction, you do not get the same distribution as you would for the opposite charges, which is fairly weird. So it also violates charge conjugation invariance. Now, that gets really interesting because we proved the CPT theorem that the combination of charge conjugation, parity conjugation, and time reversal invariance that's Lorenz invariant. That leaves like any sensible field theory of your particles unchanged. And so people believe quite firmly that the combination of all three of those should be conserved. But further experiments with the weak interaction show that the combination of charge conjugation and parity is ever so slightly violated. Not nearly as strongly as parity. Parity is actually maximally violated. And that's going to help us write the correct Lagrangian for the leptons. But the combination CP is called CP invariance is very weakly violated, which leads to the claim that T, time reversal invariance, must also be violated. That's got big consequences for the early universe. It allows us to say that a slight imbalance in time reversal invariance can lead to slightly different numbers of particles and antiparticles. And it can explain the abundance of particles over antiparticles in the current universe. The popular picture, and I don't know how much actual data there is for this, but the idea is that you produce huge numbers of particles and antiparticles. But this slight time reversal asymmetry leads to more of one type than the other type. And the type that's in greater abundance is what we call the normal matter, not the antimatter. And then you get huge, as the universe expands, it's still pretty hot, but now these particles start to annihilate one another. And the imbalance in their production leads to a slight excess of particles left over after you annihilate everything. And it's those particles that we now see in the universe. So it's a plausible explanation for the overwhelming abundance of matter over antimatter in cosmology. So people look very carefully for this sort of asymmetry, and it occurs in meson physics. So the first place you see this kind of invariance directly is with the kaon. It was probably the kaon that
Professor.
Yes.
Hey, Professor. Just
Yeah.
could I just, did anybody, speaking of the Big Bang and all this asymmetry stuff, did anybody catch Penrose's talk at the Strings conference? Like,
No, but what do you say? Tell us.
yeah. Okay. He posited that they were using data from the CMB, like that's the cosmic microwave background, to infer that you could predict the CMB based on fluctuations from a black hole that you would call a singularity. But you should watch it. It's very interesting, where he ascribes the asymmetry to Hawking radiation from a universe before ours. It's kind of trippy, but
Okay. Yeah, maybe you could.
Just on that same asymmetry, I think there's a sense of that it's connected to black hole asymmetries too.
Well, let's see. Maybe you should send that article around. That could be really interesting.
It's just a talk. If you just Google, he just gave us a talk on. I don't know if there's a formal paper attached. It's just
okay.
The final day of the Strings conference. Just Google Penrose. I guess I guess I can find it. I'll put it in the chat. Sorry.
Yeah, thanks.
It's pretty cool though. Yeah. But it's I think it's kind of relevant.
Yeah, could be.
All this to piece together.
Penrose has had quite a number of conjectures about cosmology. Not all of them have really borne out. So, we'll see. But it's really a fairly wide open question why we see matter and not antimatter. There could be some mechanism that separates it, or people have come up with some things, none of them terribly compelling. I think energy considerations, if you have a certain minimal level of asymmetry in the antiparticle production, then you're within the bounds on the amount of energy we see in the universe for that Weinberg scenario to hold up. Yeah, I don't know about the black hole picture. Yeah, could be. I'd like to see what he had to say about that. He has some fun ideas. Let me see.
Yeah, it's definitely fun. I put it in the chat.
Yeah. Okay. Yeah, got it here. Yeah. Let me copy that a second. I'd like to have a look. And whoops, let me just find a place to put it. There we go. Okay. Yeah, thanks, Alex. Cool. So you don't know. Any mechanism you come up with that produces a lot of particles and not a lot of antiparticles is a candidate. I don't think you're going to find a whole lot of data for a while. Let's see now. All right, let's see. You still seeing my screen here? So back to how to describe the violation of parity. One of the things that you find is that the it's maximal violation of parity. You know, just theoretically, it couldn't be greater than what it is. So now let's ask, well, what kind of interaction could lead to a maximal violation of parity? And the kinds of interactions we expect for fermions, I think I mentioned these before, but we can have, this is a scalar interaction or a vector interaction, or the tensor interaction is when you put the commutator here. And then anything with gamma 5 in it is going to violate parity on its own. So we have what's called the pseudo vector. And finally, the pseudo scalar, where you just put a gamma 5. So these are the things that you can stick between a pair of spinors to produce various vectors. And these are the kinds of interactions that you might get by contracting these, say, on gauge fields. You could produce different kinds of interaction. And so people have looked at all these different things, but in order to violate parity, what you can do is to write your spinor as a left plus a right-handed spinor. And those you define using these projection operators that we've already looked at. That is, so a left-handed spinor, use 1 minus gamma 5 acting on the spinor. Now, 1 minus gamma 5 is times a half is a projection operator. That squares to itself if you've got the half in there. And
the
then
writing might have froze again.
Oh, rats. Okay.
We got psi equals psi L.
Let's see. So down here, you're not seeing this.
Nope.
No. Oh, rats. Let's see. So all right, and I'll just start it again.
Yeah, that worked last time.
What's that?
That worked fine last time. Just refresh it.
Let's just do it again. Okay, so stopping the share. Hello, everybody. Good to see you, bigger. Hey, I can see you off at the side, but it's nice to see you full size. Well, full size. I mean, you're about that big, right? But you know, bigger than this. Okay, sharing again, I think, and let's screen mirroring. Yeah. Okay. And so now we
It's
get
good now.
Oh, all right. Well, there's a way to do it then. Okay, so we want to look at each of these potential interactions, but we want to see how they depend on the left and right-handed parity spinors. We can do these projections, but what we need is something that treats the left and right differently. So we need to be able to construct something, say, just out of left-handed spinors that we can put into the action without putting in the same thing for the right-handed. And of course, this projection is with a plus here. So we've met all these characters before. What we need to do now is look at something like, well, let's just start with the scalar. And I'm going to leave most of this as an exercise, but let's see, to write something like this, we're going to need to know what psi, what does psi bar look like? Well, what we mean by that is we take the dagger of psi and multiply by the projection dagger, and then we add the metric on there to turn the dagger into a bar. But remember, H in the basis we usually use is just gamma 0. That's going to anti-commute with gamma 5. So I can bring the H inside but it's going to change this to 1 plus gamma 5. Now, gamma 5 is Hermitian, 1 is Hermitian, so 1 minus gamma 5 dagger is 1 minus gamma 5. But then we recognize this as psi bar and times the opposite projection. Well, that's that tells us what psi bar psi is, because we can just substitute. All right, here we have psi left bar plus psi. Wait, let me do this differently. Let me write it as, okay, psi bar, and then the left one is going to be a half 1 plus gamma 5, and the right one is going to be psi bar times a half 1 minus gamma 5 times, and then the usual projections here for the left psi and the right. So I can certainly write all of that somewhat redundantly. But now when I carry out the multiplication, now I've got the 1 plus gamma 5 on the right here and 1 minus gamma 5 on the left there. And those are orthogonal projections. Those give 0. So that the product of those two is 0. On the other hand, 1 plus gamma 5 with a 1 plus gamma 5, it's a projection, so it squares to itself. So what I'm going to get here is I'll have a 1 plus gamma 5 with a psi. That's this one and the last one. And then we have another one that is psi bar a half 1 minus gamma 5 psi. And now, right, using the fact that these square again, this is 1 plus gamma 5 on psi, I can write as a psi r, but right, I can write this as its own square and let one of them act on psi to give me a psi right, let the other one act on psi bar, that gives a psi bar left. And then this term, I can write this as that times itself, and that's going to be a psi right bar times a psi left. And so, so psi bar psi is a product of a left bar with a right and a right bar with a left. And that tells us that, oops, we can't use that because that's not, that treats the right and left fields equally. So any admixture of that is going to be less than maximal parity violation. So you don't want to use that. And the ultimate resolution of all of this is that we're going to end up using left doublets and right singlets. So you can't write this thing in terms of those either. So so we don't write this. Okay. Anybody see what the problem is that causes? Nope. Where do we see a psi bar psi in our initial action? The mass term. Okay, we've just gone right ahead and written the Dirac action, which contains a psi bar psi, but that does not violate parity. You need to treat left and right equivalently for that term to be there. Okay, that just mucked up the entire standard model because quarks have masses, right? So we're just dealing with the weak interaction here, which always has to do with the leptons, but it also has to do with the quarks. Everything interacts weakly. So, we have to find a whole entirely different way to introduce mass into the theory. This problem is independent of the first one I mentioned, where the gauge bosons are massless. That's fine for the gluons. The gluons, so far as we know, are zero mass particles. The photon, zero mass particle, no problem. But the weak intermediate vector bosons, the W plus and minus and the Z naught, have huge masses, 80 GeV, 90 GeV for the Z naught. Those are extremely massive particles, and that's not allowed for gauge bosons. You can't do that. Well, so now we have a double problem. And actually the solution to both comes from the same general direction. The start to the solution is the Higgs particle. But we cannot put in quark masses directly as a psi bar psi combination. We have to find some new way to introduce quark masses, to introduce masses for the leptons. They have masses. Even the neutrinos now we know have masses, and the weak gauge bosons have to be given masses. So now, as an exercise, I want you to show, and let's see, where is this? This is like page 369. Each of these other objects, right? And I want you to write each of these in terms of left and right parts. And I give you the answer. What happens is, okay, so the answer for the vector particle, why is this not writing? Okay, so for psi gamma alpha, psi bar gamma alpha psi. This is jumping all around. Okay, there we go. Oh, I know what the problem. I was touching it with my fingers. Thought I was a pen. Okay, so this, it turns out, can be written as psi bar left gamma alpha psi left plus psi bar right gamma alpha psi right. Okay, well, this breaks up. You know, I could throw away that term and have a perfectly consistent vector built out of only left-handed spinners. And so that term is actually allowed. So what we need to distinguish for each of these kinds of interaction is whether or not the left and right separate this neatly or not. Well, it turns out, and you'll show pretty easily, it's a quick calculation, that the tensor and scalar, so psi bar sigma alpha beta psi and psi bar gamma 5 psi mix psi right and psi left. But the vector, this one's okay, and the pseudo vector, psi bar gamma alpha gamma 5 psi, also separates into a left and a right piece. Like this. And so we can work with just the left and right pieces of the vector and the pseudo vector. So now let's try a general linear combination of those. Oops, gamma 5 psi left. All right, and now I can form up a slightly different linear combination here. I can write a half alpha plus beta psi bar left gamma alpha 1 plus gamma 5 psi left, and a half alpha minus beta psi left bar gamma alpha. This is just taking different linear combinations. All right, so what happens here? Well, psi left has a 1 minus gamma 5 in it. All right, that's a left-handed projection, which is orthogonal to the 1 plus gamma 5. So this term is 0. And so what we get is some constant, never mind what alpha minus beta is. So we have psi left, gamma alpha, 1 minus gamma 5, psi left. And you can write that in different forms. I've given you another exercise to show that you can write that combination, if I got the normalization of a half here right, but you can write this as a gamma alpha psi and psi bar gamma alpha gamma 5 psi, right? This is a vector. This is usually it's called the pseudo vector, but it's often also called an axial vector. You probably encountered angular momentum is called an axial vector, right? It gives you an axis. So this is an axial vector, and this gives the what's called the V minus A interaction. That's essentially the unique thing that you can build that maximally violates parity. And the V minus A interaction turns out to be a good description of the weak interaction. So what that means is when we write our electroweak theory, we're going to write an action that looks something like this. We're going to have our squared field strengths, and let's see. Well, we also have the what I call the H field, and then we're going to have a sum over the leptons of something like psi bar. And we can d slash, but now we need a 1 minus gamma 5 in here times psi. So now the interaction between these fermions is only an interaction between the left-handed fermions, and the d slash. All right, let's look in detail what this d slash looks like. So psi bar d slash psi is psi bar, and these end up being left-handed. If you move the 1 minus gamma 5 back and forth, there's a gamma here, changes it to the 1 plus gamma 5, which is what gives you the left-handed psi bar. So you can, and it squares to itself, so you can put as many of them in there as you need to write this in various ways, and you should practice that a little. But then we get the we have a gamma. Let's see, how do I want to write this? Yeah, let me pull out the gamma beta, and then so we have a d beta plus I over 2, some coupling constant for the SU2. I pulled out the gamma beta, and that contracts on B beta. And then we've got those running from 1 to 3 for the weak interaction. And then we've got the hypercharge I over 2 with its coupling constant G prime and its gauge field B beta times the hypercharge Y, all times psi L. So that's now the covariant derivative, where these are left-handed fields that enter into the interaction. And then you notice these have the usual form of a current. So if we have a left-handed current, gamma beta, let's see, yeah, psi L, that gets coupled to the gauge field. There's a tau sitting in here. So I beta tau I here. So this is a gauge field with a current. So this is the conserved nether current of the SU2 symmetry, and that's what couples to the the gauge field. So in that sense, it's just like electromagnetism. But now it's everything is left-handed. Now, in order for this to interact, that spinner has to be a doublet. Notice we've got a tau in here. So the SU2 is only going to act on things that are left-handed doublets. So you have two left-handed spinner fields in here. And so far, those spinner fields are massless, even though we know that somehow they've got to get a mass. Now, we can't just do the theory with only the left-handed fields entirely, because we're unifying the electromagnetic and the weak interactions. And while the weak interactions violate parity, and so we need left-handed spinners here, electromagnetism preserves parity. And so the electromagnetism is going to need the right-handed piece. And the way we handle that is to make the, say, electron field, we include a scalar electron field, right-handed. And then for the spinner part, we have a doublet. The left-handed part, it's 1 and 2, say. So we have doublets and singlets. This still prevents us building a mass term, because you can't just combine a scalar particle with a vector particle. We've got a two-component vector and a scalar under SU2. In order to produce some scalar value term in the action for that, we're going to need another doublet to combine with this doublet. You can always multiply in the singlet. So it's perfectly fine to write something like E bar right times psi left. And that's going to be just multiplying each component here by the barred E field with psi 1 left and psi 2 left. You can do something like that, but you still have a doublet. And that doublet is going to combine with the Higgs, which I will tell you all about probably next time, because that's our time for today. I'll get these notes up soon. I've been, well, we've been doing a lot of traveling. We drove across the country and stuff. But yeah, I'll be here next Monday and tell you all about spontaneous symmetry breaking. You've probably seen that, right? It was, where you've got the Mexican hat potential and all of that. It's a fairly simple idea, but what you may not have seen with that is that that Higgs scalar is actually a complex doublet. So it's actually 4 fields, not 1. So yeah, easy to do this with a single scalar field. And all right, so it falls to the bottom of the well, but the well is actually in some 4-dimensional space. And so there's a little more to it than what you see in like intro modern physics or something. So anyway, good to see most of you here. Missing Tyler. I don't know where Tyler is, but yeah, welcome back, Alex. Glad you can join us. Yeah, thanks for sharing that article, and yeah, try to catch up on the notes. Email me if you have.
I even had just a question on this, just recent,
yeah.
today.
Sure,
So
sure.
is this like a general procedure then in coupling 2 quantum fields together, right? Is that you'll find their sector where they're interacting, isolate the other, and then quantize that sector? Because effectively we just found a covariant derivative that's giving a propagator that then has a residual quantization left over, right? So we're just trying to factor the propagator in the general form as best we can, right? Between 2. So right now we're doing it between SO3 and SU2.
Well, okay, the propagator and the interaction are different here. The propagator is usually that curl term.
It'd be the D, that's the free field, but then we'll get an interaction propagator, right? That'll be the D slash with the modification of the covariant coupling.
Let's see.
Just like we got in E&M, right?
Well,
Or then we gotta,
yes, it is just like E&M. That's right.
Mhm.
The interaction term comes from the time evolution with the interaction piece of the Hamiltonian, which is generally polynomial in the fields. So
yeah, that's weak. Yeah.
yeah, so you expand all that. Let's see.
And because we're working with one of the legs, we're working with the momentum of the one of observation. Like that's why the three others are splitting out. We're doing it's a little group symmetry basically, right? That we're isolating.
You lost me.
Yeah.
Say that again.
We're looking at the symmetry of one of the outgoing legs of a 3 or a 4 body interaction. So that's what we're quantizing off of, is the outgoing momentum in each case, right? And then we're just forming a propagator based on the field couplings that then gives us the outgoing leg that we're quantizing off of. Well, that was a lot. It's probably not dense.
You write the propagator for the free fields.
I'm talking interaction. Sorry, I'm in Hamiltonian, or I'm in Heisenberg picture.
Yeah. So the interaction. Oh gosh, let's see. I need to think back. Is let's see. What do we end up writing for the interaction terms? The gauge particles end up having a propagator. Yeah.
Yeah, I'm just thinking it really small, just like the D slash that we modified will be the thing that we're 1/overing because we're taking a derivative. So it's like polynomial factorization. It's like 1 to, so our like we'll do the Fourier transform and then we'll get a 1/D slash with all the stuff.
Yeah.
And so that's why I'm just viewing it as that. That's why you can, it's like, that's what we're quantizing.
Fermion propagator.
Yeah, the fermion.
Yeah, you certainly, you handle this a term at a time. Right. So each term in the Lagrangian gives rise to a particular diagram. And let's see,
we're like drawing our diagrams in the left. We're doing it in the left space. That was what we did here. So we just like said we can write all of our diagrams in terms of left movers.
Yeah.
Left and so like that's where we're quantizing our particles, is in the left sector. And then we found we didn't care about the right sector until we do, right?
So yeah, we need to keep those right-handed fields around, but they are not coupled to the SU2.
Right. And okay. Yeah. Okay.
Yeah. Good. Any other questions?
Is this related to the fact that we have like this type of like sector breaking, where since we have a no, that's too much of a question. I don't know. Sorry. With like that's too much of a question. I can't phrase it well enough. Okay, sorry.
Well,
yep.
Yeah, let's well, I can stick around and answer questions, but yeah, if there's anything else of general interest, happy to talk about it.
I might not be in on the 26th. I'll be out of the country.
Okay, that's 26th. Yeah, let me see. Okay, yeah, let me pull up my calendar here.
I gotta get going.
Yeah, okay, Eli.
Bye, Eli.
Yeah.
Good seeing you. We should all party some. Oh, bye.
All right. Okay. Yeah. The 26th. Yeah. Let's see. I get back home the 25th, pretty much. But okay. Let's see. Next week I'm here. I don't know what I'll be talking about the 26th. We probably only have a few more lectures before. I don't know when the semester technically ends. I know you guys are here because you're interested in this. So we can more or less go as long as we want. But I probably want to touch a bit on string theory, at least a little. But
string theory's dead. Didn't you hear? We're over it. It's done. We don't care.
Who told you that?
Loop gravity's the one. It's all like.
Oh God, who told you that?
That string conference I talked about. They're like global symmetries are dead. They're like they're just talking about doing stat mech instead of having global symmetries.
You mean
And-
local symmetries?
Having
Okay.
asymptotic symmetries are proving the way to
Okay.
quantize gravity. So stat mech has asymptotic symmetries.
Well,
but it
yeah,
doesn't
but
have-
asymptotic symmetries are, that's interesting from the string theory. point of
Okay, I'm gonna go. I'm hungry. I'm gonna
Okay,
go.
see you, Red.
view here.
Bye.
I should go too. I've got laundry. But yeah. If you have any, all those videos are on YouTube. It's pretty interesting. But so it's like, why have one string theory when you can do all of them? Is looking like where you go.
Where you
Don't-
could do all of them. I don't know. What's the claim there?
That